Today in Chem 30, we are going to talk about the basics of calorimetry, and we're doing this because this is one of our ways of directly determining the enthalpy change of a chemical reaction. Our success criteria is being able to describe the assumptions of calorimetry, describe how calorimeters function, describe specific heat capacity, and analyze word problems that use the formula of Q equals mc delta T. So we have a couple of definitions that we need to remind ourselves. First, we need to remind ourselves of the law of conservation of energy. That energy cannot be created or destroyed in physical and chemical changes. It can only change its form. So you can store energy in a chemical bond as potential energy and release it as kinetic energy, or vice versa, take kinetic energy and suck it into a bond as potential energy. But you can't get rid of it. It's just like matter. It has to, if you start with it, you have to end with it as well. You can only change its form. Thermochemistry is what we're studying right now. It's the change of energy during chemical reactions. An isolated system is then a system where neither matter or energy can move in and out. And we need this to study thermochemistry. The reason for that is that we have our environment all around us, not like the ecology environment, just the space that we're in. And if energy escapes out into the environment, it gets out into the air or the table or the lab bench or whatever, we can't measure it. We have to funnel all of the energy into something we can measure during thermochemical experiments. So that's where calorimetry comes in. Calorimetry is a technological process of measuring energy changes in an isolated system, and we do that using a device called a calorimeter. Well, what's a calorimeter? The simplest one is literally two coffee cups and a thermometer. A coffee cup calorimeter is not a perfect calorimeter. It is not a perfectly isolated system, but it's pretty close. The styrofoam and air, if you nest two coffee cups inside of each other, are actually great at insulating the environment from any temperature changes on the inside. So if we put a stopper on top, we stick a thermometer into it, we can just do calorimetry with nested polystyrene cups. We can do more calculated and accurate calorimetry using things called bomb calorimeters. The name sounds more exciting than it is. Bomb calorimeters are the most boring thing on the planet, but they are super accurate when we need to actually really precisely measure how much energy is being released or absorbed by a reaction. And we'll talk about those more later on. What happens in a calorimeter is we have a whole bunch of water inside the calorimeter, and water's nice because we can easily measure the temperature change of water. We have a bunch of water inside the calorimeter, and we're going to use water as a proxy. We are going to assume that all of the heat of the chemical reaction gets transferred into the water and none of it escapes into the environment. This is a very good assumption if we're talking about an aqueous solution chemical reaction where we're mixing two things together inside of the calorimeter. It's not as good of a one where we're doing a combustion reaction because we can't do that with the polystyrene cups. We actually have to put a beaker of water on top of whatever we're burning. And while the heat does go straight up, it's a bit trickier to try and get all of it absorbed. So sometimes this is a good assumption, sometimes it's not. This is why bomb calorimeters exist. We're also going to assume that the calorimeter is not absorbing energy itself. And you'll see cases where this is not a great assumption. It's when we have to do complex calorimetry, but we will get to that. But we're assuming that all of the energy gets absorbed by the water. None of the energy of the reaction gets absorbed by the calorimeter. We also assume that what's inside the calorimeter doesn't escape out into the environment. We're also going to make a couple of other assumptions. We're going to assume that whatever solution is inside of the calorimeter is effectively water, that it has the same specific heat capacity of water, which is 4.19 joules per gram degree Celsius. That means that every degree of temperature change we see in a sample of water is equivalent to a change of 4/1900ths of a joule per gram of the water. So the joules are both per degree change and per gram. We also assume it has the same density as the water, which we're going to end up using a lot. Just a reminder, the density of water is 1 kilogram per liter or 1 gram per milliliter. And we can make this assumption because dilute solutions are so close to water that it becomes a rounding error. It's only super concentrated solutions that these numbers are going to change in. And of course, because we know that chemical reactions are going to conserve matter, we're also going to assume that matter within the system does get conserved. What we can do with this then is we can use specific heat capacity calculations to actually experimentally determine how much energy is being lost or absorbed. The formula we can use for this is Q equals mcΔt. Q in this case is the energy of the calorimeter. Effectively, this is the inverse of delta H. Q is going to be equal to negative delta H, and often I don't bother with signs when we're talking about Q and delta H. I'll actually assign the signs after the fact. So energy, Q or delta H, whichever one you want to call it, is equal to mcΔt. M is mass of whatever thing's temperature is changing. Most of the time this will be water. Read the question carefully though, because it's not always water. So the mass of whatever is changing is M. The specific heat capacity of whatever is changing is C. If it's water, it's going to be 4/1900ths of a joule per gram degree Celsius. But again, it's not always water, so read the question carefully. And there's other specific heat capacities in your data book. And then delta T, of course, is change in temperature. Now you will notice this time, this is in Celsius. Do we have to convert it to Kelvin? No, we do not, because we're measuring the change in temperature, not the absolute temperature, like we were doing with gases last year. So there is no need to convert into Kelvin, and in fact, delta T is going to be the same whether it's in Kelvin or Celsius, because 1 degree Celsius is equal to 1 degree Kelvin, and it's just the start and end point that you're moving. So no need to add 173.15 to all of the Celsius calculations. We can just get on with it. And as an aside, that's why temperature is lowercase t this year, not uppercase T as well. And then the other thing that's really important to remember with this is that when you do this calculation, you're going to do the calculation to solve for joules, not kilojoules. All of the measurements we've done so far are in kilojoules. In fact, most of the time our measurements will be in kilojoules. And you can bet your bottom dollar that you're going to have some false answers on the diploma that are just simply separated by a factor of 1,000 to check did you convert joules to kilojoules. So pay really close attention to your units. I will show you some tricks for being able to get around that as well. So all energy gained or lost by the chemical system will be gained or lost by the calorimeter, the water inside of it, not the actual cup container. All of the material in the system will be conserved. We're going to use the specific heat capacity of water when we're dealing with a solution. So 4/1900ths of a joule per gram degree Celsius, and we'll use the density of 1 kilogram per liter as well. And that will give us all the information we need in order to do some calorimetry calculations.